we're going to talk about the two types of functions we've already learned. So one of those is linear and the other one is quadratic. So first thing, we can represent all these in 4 ways: a word problem, an equation, a table, and a graph. So that's 4 ways that we can talk about functions. So let's talk about first linear. So here's an example of a word problem that's linear. You are driving to visit your best friend in Gulfport. Since you have a long drive ahead, you turn on your cruise control. The cruise control keeps your car traveling at a constant rate of 60 miles per hour. So the word in this that tells me that it's going to be linear is constant. So that word constant, automatically I should be thinking this is going to be a linear equation. If I'm given the equation, which would be like right here, I'm taking my hours and multiplying each one by 60 to decide after how many hours, how many miles have I driven. How do I know that equation is linear? Well, this variable has an exponent of, oops, sorry, that was meant for everybody. An exponent of 1. So if there is an exponent of 1 or there's not an exponent, because we don't need to necessarily write the 1, it is linear. If we look at a table, so here's a table of the same situation. So after 1 hour, I've driven 60 miles, 2 hours, 120, 3 hours, 180. How do I know this table is linear without me telling you? Well, we can look at the change here, the rate of change. It's changing by the exact same number every time. What's it changing by? 60. We're adding 60 every, not 160, adding 60 every time to get the next number. So if I'm given a table, that's how I could tell if it's linear. Last thing is the graph. Well, how do I know if that graph is linear? It's a straight line, linear, right? Straight line. So as long as it makes a straight line, it would be considered a linear graph. So are we good with linear? Okay, so let's look at quadratic. So that was like parabolas. That's what we just finished. So if I look at this word problem, you are observing the height of a ball as it is dropped from a 100-foot tall building. Because of the force of gravity, the more that time that passes, the faster the ball travels. The ball does not travel at a constant speed like your car in cruise control. Well, there's a couple things that tell me that this is going to be a parabola, but the one key thing is gravity. If there's gravity involved, it's going to pull that object faster after a certain amount of time. So that's what creates that parabola shape. For the equation, how do I know that equation creates a parabola? That's squared. If it has an exponent of 2, that is going to be a parabola. A table is a little bit more difficult to tell, but just for your knowledge right this moment in your life, just know that if the difference is not the same, so the difference between 134 and 86 is 48, and the difference between 86 and 6 is 80. Because those are not the same, you just need to assume that it is going to be a quadratic. There is like a mathematical way to tell a table, but that's not something you need to know right this moment. All right, and then lastly, how do I know if this graph is quadratic? It makes a parabola. This one makes like a piece of a parabola. So if you can imagine, the other piece would be over there. But we don't draw that because we're talking about time and height, only positive time, and in this case, only positive height. So that graph would be a parabola if it was a quadratic. Okay, so that's linear and quadratic. So today we're going to talk about something brand new called exponential. So here is an example of a word problem that's exponential. So you are performing an experiment in science class in which you start with 100 bacteria and the amount of bacteria doubles every hour. Well, doubles. That means it's not going to be constant. That means it's going to be exponential. because your new value is based on a previous value. Not yet, Selena. Just like how to tell what the zeros are, but not completely how to draw it yet. No, we're going to kind of jump back to that after we do exponentials. Good question. So when I'm saying doubles, I mean, like, if I start with 2, then I have 4, then I have 8, then I have 16, then I have 32. It increases very rapidly. You could also say triples, quadruples. I don't know if quintuples is a word, but I'm going to call it that. Quintuples, multiply by 5. On the flip side, you could also be taking half or a third every time, or a fourth. On Thursday, we're going to talk about percentages of growth and decay. So instead of just like full, like whole numbers or fractions, we're going to talk about specific percentages of increases and decreases, but that won't be till Thursday. So in this case, we're doubling every single hour. So if we look at this table, if I start with 100 bacteria and I'm doubling, after 1 hour, I'm going to have 200 bacteria. After 2 hours, I'm going to have 400 bacteria, then 800, then 1600, then 3200, then 6400, and so on. If I were to graph this, before I say that, how can we tell from this table that it's exponential? Yeah, Robert.
The number keeps doubling.
Yeah, so how could we mathematically say doubling? Like what operation? Huh? Not a square. Times 2. Yeah, so the consistent thing happening in this column is being multiplied by 2 every time. So remember, linear, we are adding the same number. For exponential, we're multiplying by the same number every time. So if we look at the graph, this is what a graph of an exponential looks like. Now, it does look kind of like a parabola, except if we were to draw the left-hand side, and I want you to actually add this to your graph, it would look like this. It would almost go to a flat line. It wouldn't be all the way flat, but it would go almost to a flat line. If you've ever looked at like graphical data of like the spread of COVID, it is an exponential graph. It started out with like barely any cases, and then what happened? It went up like that. Like it literally is math. Like it is exponential, because like if I have COVID and I pass it along to Henry and Sarah, then they pass it along to 2 more people, and then those 2 people pass it along to 2 more people. It spreads extremely rapidly. So that's what creates that like increase like that. That exponential curve is what it's called. Say again.
Acceleration and speed.
Yeah, so like acceleration and speed, that's parabolic, that's quadratic, that's not exponential. And you'll see when we create an equation why. So acceleration is like a squared. This one's gonna have a different exponent, not a squared. Okay, so thinking about that, we're gonna create an equation. So if this makes you feel better, you can go ahead and cross out all of this. Bloop, 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 bye. We're just gonna use this last bullet point. So every time we make an exponential, we're going to use this formula. Y equals A times B to the X power. So your variable X is now the exponent. So all we have to do is fill in the A value and the B value. Well, what's the A value? The A value is always going to be your Y-intercept. Your B value is going to be the common ratio. And what that is just what number are you multiplying by every time. So in this case, we were doubling. So that would be 2. If it were halving, it would be a half. So let's go ahead and write this equation for the bacteria. So A value is our Y-intercept. So we could look at the graph, but it's kind of hard to tell, especially because the scale is 800. So let's look at the table. Our Y-intercept is when X is 0. So where is that happening? 100. Also could be referred to as your initial amount. So we had initially 100 bacteria. So that's our A value. So we're going to write Y equals 100 times my B value. So what was I multiplying by every time? 2. And then we're going to have the X power is our exponent to the X. So that would be the equation for this exponential. Now, what this helps us do is, let's say I want to know how many bacteria are going to be left after 14 hours. So that means instead of an X, I would want to replace it with a 14. Now, you could sit there and multiply by 2 14 times. I don't want you to do that. So everybody take your calculator. Type in, well, first of all, what order are we going to do this in? Say again. The exponent first. Then at the end, we're going to multiply by 100. If we follow order of operations, we need to take 2 to the 14th power first, then multiply by 100. Okay, so type in a 2. And we haven't used this button yet, but right above the C, the blue C button, there's an X to the Y power. Everybody see that button? Click that. Nothing happens. Just click it. And then type your exponent, which is 14, and hit equals. You should get 16,384. And then you're going to take that number and multiply by 100. And I'll repeat in just a second. And you should get 1,638,400. So what I'm saying is you're going to type your exponent or your 2 to the 14th. So 2, hit that XY button right above the C, 14, and then hit equals, and then multiply by 100. So after 14 hours, you have 1,638,400 bacteria. So on your own, you don't need to show me your answer, but I want you to figure out how many bacteria are going to be left after 20 hours. After 20 hours, how much bacteria are going to be left? Do you have, Dinon, do you have this calculator? Okay, so type your 2 right above the blue C button. There's like an X to the Y power button. Click that. Do you see that? So then type a 2 and then type your 20. And you should end up with, and then hit equals, you should end up with that number right there. Okay. And then obviously got to multiply by 100 after that. Oops. Okay, so you should have gotten, let me double check, times 100, 104 million. 857,600 bacteria after 20 hours. That's a lot. I mean, bacteria are small, but most. So that's a lot though. All right, so let's remember our bell work question. How much money did I initially ask for? 1 penny. And I'm doubling it, correct? So this number would be 2. Now, you would think that you'd be raising it to the 30th. But you're actually going to raise it to 1 less than that. And the reason is I'm already taking into account my first day, right? My first day, how much did I make? 1 cent. This value right here usually stands for 0 days, but on 0 days I have how many cents? 0. So I need to at least look for my initial amount being after my first day. So I'm doubling that for how many more days? I'm doubling it for 29 more days, if that makes sense, instead of 30 more days. So I want you to try that. 2 to the 29th power. And then multiply by 0.01. You should get the 5,000,000 368,000, blah, 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 blah. So instead of sitting there having to multiply by 2 every time, you can now use this formula instead. So we're going to look at some graphs and tables and just create the formula. So I'm using my A value and my B value. So let's look at this first. We have a table representation and a graph. So we can use either or. So what would be my A value? Remember, A is where my Y-intercept, where I cross the Y-axis, or if you look at the table, it's where X is 0. So what number is that happening at? Timesing by 3 every time. So that would be times 3 to the X power. 4 times 3 to the X power. Okay, I want you to go ahead and look at, I want you to try the next one, number 2. Just try and write the equation. You could be multiplying by something that's not a whole number, so keep that in mind for your Y column. I'll give you a minute or 2 to do that. All right, so what was my Y-intercept? 2, because that's where my X value is 0, or you couldn't really look at the graph on this one because the scale is too large. What am I multiplying by? 1/2. Timesing by 1/2. Yes, it's also dividing by 2, but we have to talk about it as far as multiplying by 1/2. And I know someone's going to say, could I write it as 0.5? No, I don't have a good reason why. I just said that. Okay, so write it as, no, I do have a good reason. What if it was multiplying by 1/3? Are you going to put 0.3 repeating in your equation? No, you're going to put 1/3. So I would appreciate it if you were just consistent with your fractions. So why would I use this? Well, I think most of you in science have talked about carbon dating or half-life. Yes? Okay, so this is exactly how they calculate how old something is. So let's say I find a fossil and it has a specific amount of carbon. I don't know what they use for fossils. I assume it's carbon because that's like the only radioactive material I can think of. And I use that to see how much is left and use this equation to figure out how old that thing is. Like scientists aren't just like dinosaurs are 100 million years old because they feel like it. Like they use actual math calculations to figure that out. Not just dinosaurs, but like all things that have radioactive material in them. They use that half-life idea to calculate how old something is. So that is one of the ways that you can kind of use this in a real life situation. Okay, before we start making some graphs of our own, we're gonna match these 4 to 4 possible graphs. Before we do that, I have a little bit of an issue with 2 of the answers, the first one and the third one. Why do you think I have an issue with the first one and the third one? Not necessarily. The second and the fourth are also opposites.
Oh, does it have a multiple in like the front?
Yeah, it doesn't look like it has a Y-intercept, but it does. And so I'm going to encourage you, if it doesn't have something, where's my pen? If it doesn't have something written at the front for you to write something, what do you think I'm going to have you write? Why 1? If there's nothing, then it's 1. What can we multiply? Yes, you're right, it is 1, but the reason is we can multiply anything by 1 and not change the value, right? So I'm actually going to change that first one to 1 times 3 to the x. And the third one I'm going to change to -1 times 3 to the x. So that negative is not with the 3. If it were, it would be written like this, and it's not. The negative is out in front of the 3 without parentheses. So we're going to, that's indicating -1 times that number. So they all have a 3 to the x. So all I care about is where are they crossing the y-axis? That is the other number that we're worried about. So if we look at the first graph, where is that crossing the y-axis at? -2. So it would have to be f of x equals -2 times 3 to the x. There's not another option because it crosses at -2. So I want you to try and match the other 3 graphs based on their y-intercept. Okay, the second graph, if you look at it, it crosses at -1. So that would be f of x equals -1 times 3 to the x. This one crosses at 2. So that would be f of x equals 2 times 3 to the x. And the last one crosses at +1. So that would be f of x equals 1 times 3 to the x power. Yeah, Trey.
What if one of them has like the same y-intercept? What would you do then?
So then you'd have to look at the other points on the graph. And that, we're about to make some graphs, so keep that question in mind until after we do that and see if you still have the same question. Okay, because the 4 that we're about to do all have the same y-intercept. Okay, so just a quick review before we make our graphs. What does the A value represent? The y-intercept. And the B value? Common ratio. No, it's not always 3, Nihal. Great question. This one just happened to all be 3 to the x. Remember, that's like if you're tripling. If you were doubling, it would be 2 to the x. If you're taking half, it would be a half to the x. I just made all, they just made all those the same. What would be the x-intercept? Oh. What would be the x-intercept? Meaning, where would it cross the x-axis?
Never.
0 would be right there. It's never going to. It's going to get really close. Like if you graph this in Desmos and like zoomed in as much as you could and like went to the, on this graph all the way to the left to like -30 million, -100 million, it still wouldn't cross the x-axis. And I'm gonna show you why. Take your calculator. So this graph looks like we are tripling every time. So this one is 3 to the x. So if we're going the opposite direction, what's the opposite of multiplying by 3? Dividing. So I want you to take 1 and divide it by 3 and just keep dividing by 3. Like just type in your calculator like a bajillion times. Tell me what happens. Yes, Lena, I'm getting there. You should get a negative exponent, but that just means it's a really small number. Did you get up to 100? Go ahead. What'd you say?
I said I hear.
Oh, because I think these calculators aren't smart enough to go past the negative 100. I'm trying to get an error and see what happens. Yeah, mine event. Yeah, these calculators aren't smart enough to go past the negative 100. If you divide stuff by a number, are you ever going to be equal to 0? Unless the number is 0. You're always going to be left with something, right? 3 divided by 3 is 1. 1 divided by 3 is a third, then a ninth, then a 27th, then or 1/27th, then a 1/81st, and then a 1, math is hard, 2 43 thirds, and then a 1 7/29ths. It's going to get a really, really small number, but you're never, ever, ever going to get 0. So all of these exponentials are never going to cross the x-axis. If you don't cross the x-axis, can you have an x-intercept? No. Intercept literally means where it touches or crosses the axis. And this is not going to touch or cross the axis. So please keep that in mind, especially when we're drawing our sketches. Again, your sketches don't have to be perfect, but make sure that it doesn't cross the x-axis when you do. All right, so let's make our first sketch. Y equals 2 to the x. The only thing I'm going to change before I graph it is I'm going to make this y equals 1 times 2 to the x. So we're always going to plot our y-intercept first. So what is our y-intercept? 0, 1, yep. And how we create the rest of the graph is we're going to think about this. We're doubling to get the next value because it has 2 to the x. So what's double of 1? 2. So my next point is going to be at 1, 2. What do you get if you double 2? 4. So your next value is 2, 4. What do I get if I double 4? 8. So my next number is going to be at 3, 8. What happens if I double 8? 16. Obviously, that's going to start going off of my graph. So based on these points, we can sketch the graph. So it's going to look like this. And that doubling is what gives it that shape. So like the ones before where it was 3 to the x, we were tripling. So our second point wouldn't have been at 1, 2, it would have been at 1, 3 instead, and then 2, 9, and then so on. Okay, so let's answer these questions. So if we're reading from left to right, is our graph increasing or decreasing? Increasing. It's obviously increasing because I started with 1 and I'm doubling. If I'm doubling a positive number, I'm going to get a bigger number. Now, these two things are talking about the ends of the graph. So this one, as x increases, is talking about the right-hand side where the bigger numbers are. So this arrow right here, where is it going towards? Up. Okay, we're good with that. We don't want to say up though. Okay, it is increasing, but what number is up? I hate saying number. What thing is up? Infinity, right? It's going to keep going towards infinity forever and ever and ever. I could double 1 an infinite amount of times. So how we're going to say its behavior, meaning where's that arrow pointing? Y is going towards, and I use an arrow, infinity. So that's talking about the right-hand side of that graph. And I know that it's the right-hand side because that's where my x values are increasing on the right. Now, the other question is what's happening on the opposite side? So where is this left-hand arrow getting very, very close to? Well, it's not going to cross 0 though, remember? Yeah, like it's never going to cross the y-axis. So it's getting really, really close to 0. So we say that it's going towards 0. Never going to touch 0. It's just going to get really, really close to 0. So when you talk about the ends of your exponential, one of them is going to go to 0. The other one's going to go to infinity. Those are your two options. It's never going to look like this. It's never going to look like this. It's going to be one is going to be going up and one's going to be going towards 0. Okay, so let's look at the next problem. This one's half to the x power. So we're going to rewrite it as 1 times half to the x power. So we're going to start at 0, 1. And we're going to take half every time. What's half of 1? 1 half. What's half of a half? 1/4. That's going to be kind of difficult to graph accurately. So let's think about the points on the left. So 1 is half of what number? 2. 2 is half of 4. And 4 is half of 8. So this exponential is going to look like that instead. What made it flip directions than the first one?
It's dividing now.
Well, not dividing. Yeah, well, I'm multiplying, but I am dividing by 2 technically, but I want to talk about just the multiplication. What am I multiplying by? Specifically a fraction that's less than 1, right? So I'm multiplying by something less than 1, so my numbers are going to get smaller. If I'm doubling, my numbers are going to get larger. So that half is what makes the exponential change direction. So if I'm looking left to right, am I increasing or decreasing? Decreasing. Remember, I'm taking half, so I'm going to be decreasing. And then we want to talk about the 2 ends. So on the right-hand end of the graph, where am I going to? 0. I'm getting very, very close to 0. On the left-hand side of the graph, I'm going to infinity. Okay, so those are 2 options of our graph. Our x-intercept is positive, and then we either have something that's going up when it's a whole number bigger than 1, or we have something that's going down when it's a fraction smaller than 1. So let's look at 2 other types of graphs. So in this case, my y-intercept is a negative. So we're going to change this to y equals -1 times 2 to the x power. So again, still going to start on my y-axis at what point? 0, -1. And again, I'm doubling. What's double of -1? -2. What's double -2? -4. What's double -4? -8. So this graph should look like this instead. So notice how it flipped from being above the x-axis to below the x-axis. And what does that? Yeah, that negative y-intercept is what makes it flip to underneath the y-axis or x-axis. So if we read from left to right, am my values going up or down? Down. So we're decreasing. Obviously, if I'm doubling a negative number, I'm going to get a bigger negative number. It's going to go down. What is happening on the right-hand side? Where is it going? Negative infinity, exactly. It's going to negative infinity. All that negative infinity means is the biggest negative number I can think of. Negative what? That's the biggest one. Then what's happening on the left-hand side? It's going to 0. right, so we have one more possibility. That's if my y-intercept is negative, which in this case it is, -1, and my common ratio or my b value is a fraction. So that's going to create like the last type of graph. So we had positive and whole number, positive and fraction. Then we had negative and whole number. And now we're going to look at negative and fraction. So we're going to start at 0, 1, -1, excuse me, 0, -1, because that's our y-intercept. And then we're going to take half. What's half of -1? -1/2. What's half of -1/2? -1/4. So if we talk about the other value, the other way, bless you, -1 is half of what number? -2. -2 is half of -4. -4 is half of -8. So if we sketched this graph, that's what it would look like. Okay, so if we're looking from left to right, is it increasing or decreasing? It is increasing. Even though it's a negative, it doesn't matter. It's still going from here up, so that would be increasing. So on the two sides of the graph, on the right-hand side, where is it going? Towards 0. And then on the left-hand side, it's going towards -infinity. Okay, we're just gonna kind of summarize all of that information, the 4 different types of graphs in this beautiful table, so that you can look back at it if you need to. So when we have a positive y-intercept and the common ratio is a bigger than 1, not a fraction, it is going to, and this is the first graph we made, it was increasing. On the right-hand side of the graph, y was going towards infinity. And then on the left-hand side of the graph, y was going towards 0. Now, the second graph was very similar. The only difference was it was flipped. And that was because that common ratio was a fraction. So it was decreasing. And my two ends switched. Now the right-hand side was going to 0. And the left-hand side was going towards infinity. So that was the second graph that we made. The third graph is when my A value was negative, my y-intercept, and my B value or my common ratio was bigger than 1. So that was decreasing still. And the right-hand side of my graph was now going towards -infinity. And my other side, my left-hand side of the graph was going towards 0. All right, and then the last option is going to be the exact opposite of the third option. So it's going to be increasing. And then my end behavior switched. So my right-hand side was going to 0, and my left-hand side was going towards -infinity. And that was the fourth graph that we made. All All right, before we kind of break for lunch, I want to look at two problems from the next, we're not going to do the entire next topic. It's unnecessary, but I do want to look at two of those problems before we do that. So I want you to look at the first one. It says 2 to the x plus 2 power. I have an issue with that because I want the x to be by itself as an exponent. I don't want an addition, subtraction, multiplication, division in the exponent. So here's what we're going to do, and I'm going to hopefully refresh your memory. What would you do if it said x squared times x to the 6th power? You would add them. That we did that back in like September, October. So that would give me x to the 2 plus 6, which would be x to the 8th. Everybody good with that part? Okay, so we're going to use that same idea to rewrite this. So those exponents are being added together. So I can essentially go the opposite direction. I'm going to put the x with the 2, and I'm going to put the 2 with the 2. And I want you to see the relationship between these two and these two. So all I did was I started with two things being added together, and I kind of split those two things up with each of my 2's. We can calculate this. What is 2 to the 2? 4. And I still have 2 to the x power. So that is something that we know how to graph. Where am I going to start on my y-intercept? 0, 4. And that 2 to the x tells me that I'm going to do what every time? Multiply by 2. So what's 4 times 2? 8. 8 times 2 would be 16. Again, going off the graph a little bit, but you could sketch that with those 2 points if you want. All right, and then we're going to look at the very last problem on the beat the test. So if you want to flip over there, and then we'll be done for now. So similar type of problem, we're trying to match each one, at least 2 of those with 8 times 2 to the x. Now, let me tell you one thing that's going to make me want to throw this pen at your face. If you pick only one answer, you're just telling me you want to get it wrong. Because if it's a select all apply, how many have to be correct? At least 2, not, but can't be all of them, right? So the most that could be correct here would be how many? 4 of them, right? So we could have 2 answers, 3 answers, or 4 answers for this problem. Another thing that makes me want to throw this pen at you is people that leave multiple choice questions blank. Again, if there are 4 answers, what's the percent that you get it right if you guess? 25. What's the percent that you get it right if you leave it blank? 0. I like 25% chance of getting it right better than 0% chance of getting it right. So again, if you only get one possible answer, at least mark a different one so that you at least give yourself a chance of getting it correct, okay? Because I saw when I was looking at the algebra nation stuff, some people got them wrong because they answered a select all and apply with one answer. That's frustrating for me, okay? Okay, so let's look at the first one. So 2 to the x to the 3rd power. So if we have an exponent to an exponent, we're going to multiply those things together. So 2 to the 3x. Well, you can calculate what 2 to the 3 is. What's 2 to the 3rd power? 8. So that would give me 8 to the x. Is 8 to the x and 8 times 2 to the x the same thing? No, they are not. So that one would be incorrect. The next one says 2 to the 4x. Well, what's 2 to the 4th power? 16. Is 16 to the x the same as 8 times 2 to the x? No. You cannot multiply these together and just stick that exponent on it. Because if you followed order of operations, what would you do first? 2 to the x, then multiply your answer by 8. This and this are not the same thing. They're not the same. So that one's wrong. So let's look at the next one. 2 to the x plus 3. So this is similar to the one we just looked at. So we can break this up into 2 to the x times 2 to the third. What is 2 to the third? 8. 8 times 2 to the x power. Are those the same thing? Yes, they are. Same as this, yes. All right, let's look at the next one. So I have 2 times 2 to the 2x. Well, 2 to the 4 times 4 to the x, the same as 8 times 2 to the x. No. So by process of elimination, what happens with the last one? It has to be right, but let me just show you how it is right. So I have 4 times, and I have 2 to the x plus 1. So we can break that up into 2 to the x times 2 to the first. What's 2 to the first? 2. 4 times 2 would be 8 times 2 to the x, which is the one what we were looking for. So the third one and the fifth one would have to be right. I'm going to leave that up for a second.